Welcome to today's School of Computing lecture. I am Dr. Alaa Jabbar Almaliki, and today we are analyzing the mathematics behind cybersecurity analytics. Every single second of the day, a massive modern enterprise network generates tens of thousands of isolated, disconnected data fragments. Security Information and Event Management Systems, or SIEMs, capture millions of these logs daily. This volume entirely exceeds any human capacity to read, process, or contextualize manually. Without a mathematical methodology to process this volume, coordinated attacks and hidden threats remain invisible to security analysts. They are buried in the noise. Raw data without structural analysis provides zero intelligence. We require computational models to organize it. Descriptive analysis serves as our foundational method for extracting threat intelligence from these chaotic SIEM environments. We are not attempting predictive guesswork here. Descriptive techniques do not attempt to forecast the future or guess what an attacker might do tomorrow. The true purpose of descriptive analysis is to establish ground truth situational awareness. It answers exactly what is happening in the data right now. We achieve this structural organization through two distinct techniques: association analysis and clustering. By mathematically identifying the patterns and behaviors within massive log environments, analysts move from reactive guessing to evidence-based threat understanding. Let's start with association analysis. This is the technique used to discover relationships, or co-occurrences, between variables across massive datasets. We look for a pattern where, if event A occurs, event B is likely to occur. To transform this into verifiable proof, we require three metrics. The first is support. Support calculates the frequency of the occurrence within the data. The second is confidence. This measures the statistical likelihood of the association actually holding true when event A happens. Finally, we calculate lift. Lift measures the definitive strength of the relationship, proving the connection is not merely random chance. When combined, these three metrics allow a computer scientist to mathematically prove that two seemingly isolated network events are distinctly linked. Let's apply this to a real-world cybersecurity application, detecting a coordinated attack. We establish event A. Our SIEM system detects a sudden spike in failed login attempts originating from multiple different IP addresses. Shortly after, we observe event B. The system logs an account lockout or a privilege escalation event on the target server. Association rules connect these two events, generating the logic: if failed attempts increase across distributed IPs, an account lockout or escalation is likely. Association analysis operates as attack cartography. It takes isolated security alerts and structures them into a verified, actionable attack chain. We now shift focus to our second analytical technique: clustering. Clustering is an unsupervised learning technique. It does not rely on pre-existing threat signatures or human-provided labels to categorize data. The algorithm groups data purely on inherent spatial characteristics. Items in the same cluster are mathematically similar, and items in different clusters are distinct. The field relies on several algorithmic models to achieve this, including k-means clustering, hierarchical clustering, and DBS-scan. As massive amounts of new data enter the system, it continuously segregates into these established groups based entirely on its traits. This unsupervised clustering creates order out of chaos, providing a mathematical baseline of what normal behavior looks like on a specific network. We can apply this clustering concept directly to a dataset of network traffic. In this traffic table, Cluster 1 and Cluster 2 represent standard, benign baseline activities. These capture normal web browsing and routine video streaming. Then we identify Cluster 3. This captures suspicious spikes, unusual access times combined with high volume activity, visually isolated from the normal groups. This spatial isolation is critical for defense. It detects zero-day threats and insider attacks without needing to know what the specific attack is in advance. Because malicious users behave differently than normal users, their data mathematically forces them into these isolated anomaly clusters. An attacker cannot hide their mathematical variance from the established baseline. This makes clustering highly effective for defeating novel cyber threats. Descriptive analysis builds a comprehensive threat landscape. A dashboard displays a clustering scatterplot on the left and an association node map on the right. Clustering groups unknown behaviors to isolate new malware variants. Simultaneously, association analysis maps transactions to geographic locations to trigger fraud alerts. When combined, these two techniques allow network monitors to detect highly complex, distributed, coordinated attacks, such as massive botnet activity. Human analysts cannot predict the future of cyber threats until they completely understand the hidden structures of their existing data. Association and clustering are the non-negotiable foundational models for achieving that ground truth awareness. Ultimately, descriptive analytics takes millions of raw, unstructured logs and mathematically exposes the exact nature of the digital battlefield.